Good evening, everyone. I hope you are all doing well and are ready for a journey unlike any other. Tonight, we are going to travel back through the vast corridors of time to witness the greatest story ever told, the story of our home, the Earth. From the violent birth of stars to the very ground beneath your feet, we will explore 4.5 billion years of fire, ice, and the relentless spirit of life. So, find a comfortable spot, settle in, and let's begin. Chapter 1. The Forge of Creation. Subject: the Hadean Aeon and the Birth of a Planet. Section 1. The Silence Before the Storm. In the beginning, there was no Earth. There was no sun, no moon, and no stars that we would recognize today. Imagine, if you will, a vast, cold, and silent void. This was the Great Nebula, a titanic cloud of hydrogen gas and microscopic dust particles, stretching across light years of space. It was the wreckage of a long-dead star that had exploded millions of years prior, leaving behind the raw materials for a new world. For eons, this cloud drifted. But gravity is a patient sculptor. Slowly, almost imperceptibly, the center of this cloud began to thicken. A knot of gas formed, pulling in everything around it. As the density increased, so did the heat. Friction between gas molecules created a rising temperature that eventually reached a tipping point. In a violent, beautiful instant of nuclear fusion, the sun ignited. The solar system was born in a flash of light that cleared the surrounding gas, leaving behind a spinning disk of dust and rock. This disk, known as the protoplanetary disk, was a chaotic nursery. It was here, amidst the screaming winds of the young sun, that the story of Earth truly begins. Tiny grains of dust, no larger than a speck of smoke, began to collide. Through static electricity, they stuck together. These clumps grew into pebbles, the pebbles into boulders, and the boulders into planetesimals, rocks miles wide with their own gravitational pull. Section 2. The Age of Fire and Iron. 4.5 billion years ago, Earth was not a home. It was a monster. It was a sphere of liquid fire, a world of pure magma. The constant bombardment of asteroids and the decay of radioactive elements trapped inside the planet created a heat so intense that the very rocks melted. During this era, known as the Iron Catastrophe, a fundamental change occurred that would determine the fate of all future life. The Earth was so hot that it was entirely liquid. Gravity pulled the heaviest elements, molten iron and nickel, down toward the center. This sinking metal formed the Earth's core. The lighter, rocky material floated to the top, forming the mantle. This core is the heart of our planet. Even today, billions of years later, it remains as hot as the surface of the sun. More importantly, the movement of this liquid metal core created a massive magnetic field. This field acts as an invisible shield, wrapping around the Earth and protecting it from the sun's lethal solar wind. Without the Iron Catastrophe, the sun would have stripped away any atmosphere we tried to form, leaving Earth a dead, dry husk like Mars. Section 3. The Theia Cataclysm. Just as the Earth began to develop a thin, fragile crust of solid rock, it faced its greatest threat. A rogue planet, roughly the size of Mars and named Theia, was on a direct collision course with our world. The impact was a moment of supreme violence. The two planets did not just collide, they merged. The energy released was enough to vaporize billions of tons of rock. Earth's outer layers were blasted into orbit, forming a ring of red-hot debris. Over time, this debris coalesced under the force of gravity to form the moon. The moon is more than just a light in the night sky. It is our cosmic stabilizer. Its gravity created the tides in our oceans, and, more importantly, it stabilized the Earth's tilt. This tilt is what gives us our seasons: spring, summer, autumn, and winter. Without the moon, the Earth's axis would wobble uncontrollably, leading to chaotic weather patterns that would make complex life almost impossible to sustain. Section 4. The Hadean Underworld. We now enter the Hadean Aeon. Named after Hades, the god of the underworld, this was a period of Earth's history that lived up to its name. The sky was a dark, bruised purple or a hazy red. The atmosphere was a toxic soup of carbon dioxide, nitrogen, and sulfuric acid. There was no oxygen to breathe. Volcanoes covered the surface, some of them hundreds of miles wide. They pumped out endless streams of lava and gas. The ground was a patchwork of black basalt rock and glowing red rivers of fire. The sun, though younger and dimmer than it is today, struggled to pierce through the thick, smog-filled atmosphere. Yet, even in this nightmare, the seeds of a garden were being sown. As the Earth continued to radiate its heat into the cold vacuum of space, the temperature of the crust finally dropped. For millions of years, water had existed on Earth only as superheated steam in the atmosphere. But as the planet cooled, the steam began to condense. Section 6. The Late Heavy Bombardment. Just as the Earth had finally settled into its new identity as a water world, the heavens turned hostile once again. In the outer reaches of the solar system, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were engaged in a gravitational dance. As their orbits shifted, they disturbed a massive reservoir of icy rocks and asteroids known as the Kuiper Belt. This cosmic disturbance sent millions of projectiles screaming toward the inner solar system. For a period of nearly 300 million years, Earth was under siege. This era is known to scientists as the Late Heavy Bombardment. If you were standing on the surface of the Earth during this time, the sky would rarely be clear. Every few decades, a flash brighter than the sun would streak across the horizon, followed by a shock wave that would boil the very oceans. Asteroids the size of cities slammed into the seabed. These impacts were so powerful they would vaporize millions of tons of water instantly, sending plumes of steam back into the atmosphere and resetting the cooling process. But these death rocks carried a secret cargo. Within their icy hearts were complex organic molecules: carbon, amino acids, and nitrates. They were the chemical seeds of life, being delivered to Earth's new oceans like a cosmic delivery service. The bombardment was a baptism of fire and ice, ensuring that the oceans were not just water, but a primordial soup, rich with the ingredients of biology. Section 7. The Alchemy of the Abyss. As the bombardment slowed, the Earth began to develop a new kind of chemistry. Deep on the ocean floor, far away from the sun's reach, the crust was cracking. Because the Earth's interior was still incredibly hot, seawater would seep down into these cracks, where it was heated by the magma below to temperatures exceeding 400 degrees Celsius. This superheated water, packed with dissolved minerals like sulfur, iron, and magnesium, erupted back out into the ocean through hydrothermal vents. These vents looked like underwater chimneys, belching black and white smoke into the dark abyss. In these dark, high-pressure environments, a miracle of alchemy occurred. The chemicals from the vents and the chemicals delivered by the asteroids began to react. In the tiny, microscopic pores of the vent rocks, molecules began to organize. They formed membranes. They began to store energy. They began to replicate. This was the transition from geology to biology. In the total darkness of the deep sea, fueled not by sunlight, but by the internal heat of the Earth, the first living cells were born. They were simple, single-celled organisms, but they were the ancestors of every plant, animal, and human that would ever live. Section 8. The movement of the Earth, plate tectonics. While life was taking its first breath in the deep, the very foundation of the Earth was beginning to move. Up until this point, the Earth's crust was like a solid eggshell, but the heat trapped in the mantle was too great to be contained. The mantle began to churn in slow, massive circles known as convection currents. This internal engine began to pull the crust apart. The solid shell of the Earth cracked into several massive pieces, which we now call tectonic plates. This was the birth of plate tectonics, the Earth's ultimate recycling system. These plates began to slide, crash, and dive beneath one another. Where plates crashed together, the first true continents were pushed up from the sea. These were not the continents we recognize today, but small cratons of granite, light, buoyant rock that floated on the heavier mantle like rafts. For the first time, there was dry land that wouldn't melt back into the sea. This movement also regulated the Earth's temperature. By swallowing carbon dioxide from the atmosphere and burying it deep underground through subduction, the tectonic plates acted as a global thermostat, preventing the Earth from becoming a runaway greenhouse like Venus. Section 9. The blue sky and the first dawn. As the continents grew, the atmosphere began to clear. The heavy, dark haze of the Hadean was replaced by a thinner, more transparent sky. The carbon dioxide levels were dropping, and nitrogen began to dominate the air. If you could stand on a granite cliff 3 billion years ago, looking out over the green oceans, you would see a sun that was about 70% as bright as it is today. The moon would look enormous in the sky, still much closer to Earth than it is now, causing massive tides that swept miles inland and back out again. But there was still something missing. The air was silent. There were no birds, no insects, not even the sound of wind through leaves, because there were no plants. The only sound was the crashing of waves and the roar of volcanoes. The land was a desert of gray and black rock. However, in the shallow waters near the coasts, a new revolution was beginning. The microbes had left the deep-sea vents and reached the surface. They were about to learn how to eat the sun. Section 10. The revolution of photosynthesis. In the shallow, sunlit lagoons, colonies of bacteria evolved a new pigment, chlorophyll. They began to capture the energy of sunlight to turn carbon dioxide and water into food. This process, photosynthesis, was the most important energy revolution in history. These bacteria gathered in massive, slimy mats called stromatolites. To the naked eye, they looked like lumpy, underwater rocks. But they were living factories. As they processed sunlight, they released a waste product, a gas that had never existed in large quantities on Earth before. That gas was oxygen. At first, the oxygen didn't enter the atmosphere. It reacted with the iron dissolved in the green oceans, turning it into rust. This rust settled on the ocean floor in thick layers, creating the banded iron formations that we mine today for steel. But eventually, the iron in the oceans was all used up. The oxygen had nowhere else to go. Section 11. The Great Oxidation Event, the first mass extinction. As the stromatolites and cyanobacteria multiplied across the coastlines of the world's shallow seas, they continued to pump out oxygen. For millions of years, this oxygen was absorbed by the earth and sea. But around 2.4 billion years ago, the saturation point was reached. The sky began to change. This period is known as the Great Oxidation Event, and while it created the world we know, it was a catastrophe for the life existing at the time. To the primitive, anaerobic bacteria that had ruled Earth for 1 billion years, oxygen was a lethal poison. It was a corrosive gas that tore their delicate chemical structures apart. This was Earth's first mass extinction. The dominant life forms were wiped out by the waste product of a new, more efficient species. As oxygen filled the atmosphere, it reacted with the methane that had previously kept the Earth warm. Methane is a potent greenhouse gas, and as it disappeared, the Earth's insulation vanished. The sky turned from a hazy, toxic red to a brilliant, clear blue. But this beauty came with a deadly chill. Without the methane to trap the sun's heat, the global temperature began to plummet. Section 12. Snowball Earth, the Long Sleep. The Earth entered its first and most severe ice house phase. As the temperatures dropped, ice caps at the poles began to grow. White ice reflects sunlight back into space, unlike dark water which absorbs it. This created a feedback loop. The more ice there was, the colder the planet became. The colder the planet became, the more ice grew. Eventually, the ice sheets met at the equator. The entire planet was encased in a shell of ice nearly a mile thick. From space, Earth no longer looked like a green or blue marble. It looked like a giant, white snowball. This lasted for millions of years. Life was pushed to the brink of total annihilation, surviving only in small pockets of liquid water near deep-sea volcanic vents or under thin patches of ice. It seemed that the story of Earth would end here, a frozen, dead rock. But the Earth's internal engine, the tectonic plates, never stopped moving. Deep beneath the ice, volcanoes continued to build pressure. Eventually, they erupted, punching through the frozen crust. These volcanoes released massive amounts of carbon dioxide back into the atmosphere. Because the ice covered the oceans, there was no water to absorb the CO2. The greenhouse effect returned with a vengeance, trapping heat until the ice melted in a global superthaw. Section 13. The Rise of Complexity, the Eukaryotic Revolution. Emerging from the ice, life did something extraordinary. Until now, all life was prokaryotic, simple, single-celled organisms with their DNA floating freely. But in the aftermath of the Great Freeze, a new type of cell appeared, the eukaryote. This happened through a process called endosymbiosis. One small cell swallowed another, but instead of digesting it, the two cells formed a partnership. The internal cell became the mitochondria, the power plant of the cell. This gave the new cell hundreds of times more energy than the old ones. With this new energy, life could afford to be complex. Section 14. Rodinia, the first supercontinent. As life evolved in the seas, the land was shifting into a new configuration. Around 1 billion years ago, the moving tectonic plates brought all the Earth's granite islands together into a single, massive landmass called Rodinia. Rodinia was a desolate, silent continent. There was not a single blade of grass, no moss, and no soil. It was a vast desert of red and gray rock, hammered by massive storms and scoured by the wind. However, the formation of this supercontinent changed the ocean currents, which in turn changed the climate. When Rodinia eventually began to break apart, it created vast new coastlines and shallow seas. This real estate was perfect for life. The breaking of the continent also washed massive amounts of nutrients and minerals into the ocean, acting like fertilizer for the evolving cells. The stage was being set for the most explosive event in the history of biology. Section 15. The ozone shield and the gateway to land. As oxygen levels continued to rise, a new layer formed high in the atmosphere, the ozone layer. For billions of years, the Earth's surface had been blasted by the sun's ultraviolet, UV, radiation. This radiation was so strong that it would shred the DNA of any organism that tried to live on land or even in the very top layer of the ocean. But oxygen molecules, O_2, in the upper atmosphere were being hit by sunlight and turning into ozone, O_3. This layer acted like a pair of cosmic sunglasses, absorbing the lethal UV rays. For the first time in 4 billion years, the land was safe. Life was no longer trapped in the deep or under the shadows of rocks. The gateway to the continents was open. But before life could walk, it had to learn to swim, hunt, and see. We are now on the doorstep of the Phanerozoic Eon, the age of visible life. Section 16. The Cambrian Explosion, Nature's Big Bang. Around 541 million years ago, the Earth reached a biological tipping point. For billions of years, life had been slow, simple, and microscopic. But suddenly, in a window of time that was a mere blink in geological terms, the oceans exploded with variety. This is the Cambrian explosion. It was as if nature had finally mastered the software of DNA and began running thousands of new programs at once. In the shallow, oxygen-rich waters of the Cambrian seas, the first complex animals appeared. These were not just blobs of jelly. They had skeletons, specialized organs, and nervous systems. This era saw the invention of the eye. For the first time, creatures could see their world. This changed everything. The world became a place of hunters and the hunted. Evolution became an arms race. To survive, you needed speed, armor, or camouflage. The tranquil garden of the Ediacaran period was gone, replaced by a vibrant, violent, and highly competitive ecosystem. This was the moment the blueprints for almost every modern animal group, including the ancestors of humans, were first created. Section 17. Trilobites and the Lords of the Ancient Seas. If you could go back to a Cambrian beach and look into the water, you would see a creature that defined this age, the trilobite. These were the first masters of the planet. Related to modern crabs and spiders, trilobites had hard, segmented exoskeletons and sophisticated compound eyes. They scurried along the seafloor in their millions, scavenging and surviving through multiple mass extinctions. But they were not alone. The top predator of this world was a nightmare named Anomalocaris. Imagine a 3-foot-long shrimp with spiked arms and a circular mouth lined with razor-sharp teeth. It was the great white shark of its day. Its appearance proved that life was no longer just about cooperating or photosynthesizing. It was about the transfer of energy through consumption. Section 18. The first backbone, our humble ancestry. Amidst the giants and the armored monsters of the Cambrian seas, there was a tiny, insignificant-looking creature called Pikaia. It was only about 2 inches long, shaped like a sliver of muscle, and swam with a side-to-side motion. Pikaia lacked a shell or spikes, but it had something revolutionary, a notochord. This was a flexible rod running down its back, the precursor to the spine. Pikaia is one of our earliest known ancestors. While the trilobites were protected by heavy armor, Pikaia's internal rod allowed for more efficient swimming and a more complex nervous system. This tiny, vulnerable swimmer was the start of the line that would lead to fish, amphibians, dinosaurs, and eventually us. Every human backbone is a direct legacy of the survival of these small Cambrian swimmers. Section 19. The Chemistry of Bone and Shell. How did life suddenly find the material to build these skeletons and shells? The answer lies in the Earth itself. As the supercontinent Rodinia continued to break apart, massive amounts of calcium and minerals were washed into the sea. Life learned to harvest these minerals, specifically calcium carbonate and calcium phosphate. This biomineralization was a turning point. It allowed life to move beyond soft tissues. Bones provided a frame for muscles to pull against, leading to faster movement. Shells provided a portable fortress. This shift turned the Earth's crust into a biological resource. We are, quite literally, made of the rocks and minerals that the Earth provided during its tectonic upheavals.